Hey, and welcome back to our little discussion of statics. This is going to be part two, and basically we want to do some examples here. So this will be the statics examples part. Let me remind you here that in the last film we said there were only two rules to this business. The first thing that we need to make sure that something doesn't move is to ensure that the sum of the forces equals zero. The second rule was just as easy. Make sure that it doesn't rotate. Make sure that the torques all cancel out. The forces cancel out, the torques cancel out. It's not going to move. It can't. So we want to lock those down both ways. Here are some examples of that. In the first one here, this is the problem that we were looking at the end of this. Remember that for every one of these, we want to pick a pivot point. I can't spell today. Pivot. That's this guy right there, right? That thing is sitting on this triangular block right there. We're going to pick that as our pivot point. Need to measure all of the distances from that point, and those are marked out here. You can see that from this point to force 1 is called D1, and that's 3 meters. From pivot point to force 2 is D2. We don't know that. It's actually what we're looking for in this problem. So I'm going to just put a little question mark right there. We'd like to know where to put this thing to balance it all up. And then force 3 is way over here. We need to measure from the pivot point to force 3. Once we've done, that's 4 meters up there. So once we've done that, we're ready to begin. There actually is a fourth force. The pivot pushes up, doesn't it? Okay, so let me just put in an arrow for that and write F pivot. We don't know what that one is. It's going to go away with the way we've set this up, so we don't really have to worry about it, but I want you to see why it goes away and what that might mean for other problems, things that we could do in the future to make our life easier. Okay, so with what we have here, first thing we want to do, pick a pivot point. We've done that. Check. Next thing we want to do is to measure everything from that pivot point. Everything is measured from the pivot. So I'm going to check that one off. Third step, sum of the torques equals 0. Each one of these forces will develop a torque around the pivot point. So I've got 1, 2, 3, 4 of these things. I'll have 4 torques. The torque is force times distance. So I would have F1 times D1. I would have the pivot times its distance. I would have F2 times the distance to F2. And then I'd have F3 times its distance. And all of that better equals 0 right there. Okay, we know most of these numbers. I'm going to go ahead and put them in. I might get a little sloppy with the units here. Let's put them in to begin with, I guess. 20 newtons times 3 meters. I've got F pivot, which I don't know, but the distance from the pivot point to the pivot point is, of course, 0. So in the end, see how F pivot times 0 equals 0? So that one went away. Sometimes we can make the force go away, or at least the torque due to that force go away by picking the pivot point right there. We'll do that later on too. F2 is 10 newtons. D2, I don't know what that is. That's what we're looking for here. Maybe we're playing seesaw, and we got 3 kids that want to play, and they need to know where to sit so that the seesaw balances. And so this third kid, F2, has come along. He wants to play, wants to get on, and they say, well, we think we can make this work, but let's do the statics and make sure here. You can see that's our only unknown. The last step here would be to get the directions of rotation. So again, I encourage you to hold your pencil at that little red X right there where the pivot is, and then push down on the left-hand side, and the whole beam is going to rotate counterclockwise. That is to say, the right-hand end will rotate up. And when I push down on the right-hand side, the right-hand end of the stick will go down. Okay? Anything that makes it rotate such that the right-hand end goes up is positive, and I would put a plus. This one's 0, so I'm not going to worry about it. But the other two make it rotate in the opposite direction. That would be negative, like that. We've got some numbers here and here. We can combine those. You can see these aren't very hard to do. 20 times 3 minus 8 times 4 gives me 28 over here. That would be in Newton meters. And then minus 10 newtons times D2 equals 0. Let's subtract the 28 from both sides. You can see when I divide by the 10 newtons that D2, negative divided by negative, would be positive. 28 divided by 10 would be 2.8. And Newton meters divided by Newton, the newtons are going to cancel out. And I'll just have 2.8 meters. The distance from the pivot point to where D2 needs to sit to make this thing balance would be 2.8 meters. That's a beam problem. Okay, right here, I'm done. That's the only unknown. Unless you want to find the force that the pivot puts on it, we could do that as well. What is that mystery pivot force right there? What does the support need to hold up? If I want that one, then I would come in here, and the only other trick that I have in statics is the sum of the forces better equal 0. So here, again, 4 forces. I like to start on the left, go to the right. I'd have a 20 newtons. I've got that pivot force. I've got 10 newtons. I've got 8 newtons, and it better equal 0. Some of these are upward forces, some are downward forces. Let's call anything that pushes up positive, anything down negative. And so the 20 newtons is downward. The pivot is up. These two are down. So that would be my equation. And it doesn't take a whole lot of arithmetic there to see that we're talking about 38 newtons of force that the pivot has to push up there in the middle. We could have done that step first, and then you brought it over into the torque equation. Sometimes it makes a difference, sometimes it doesn't. Here it doesn't. We could have done it, and if they probably don't care how much the pivot was, so you might not even have to do this part at all. But if you do, come in with your other rule, and you got it made. Here's a second example. In this case, I've got a beam. We've got walls under the two ends. So, here is a floor of a building, and I've got a wall that's holding up each end. So it looks something like that. We've got a safe about right there. And then we've got an air conditioner unit over here doing its thing like that. All right, that's the picture of the thing. You can see that the forces on this, the wall is going to push up, and the safe is going to push down, and the air conditioner is going to push down, or rather gravity is going to pull down on those two guys, and this wall is going to push up. There's actually one more force we should put in here. They gave us the mass of the beam. If they give you the mass of the beam or the weight of the beam, then they want you to put that in. The walls have to hold that up as well. And so we need to put in the weight of the beam. All of the beams that we do will be uniform beams. They're not tapered. They're not concrete on one side and wood on the other. They're uniform. That means that the weight acts dead smack in the center right there. And so, if I call the left-hand wall F1 and the right-hand wall F2, those are the two things that I'm looking for in this problem. This would be the force that the safe puts on the beam, and over here is the force that the air conditioner puts on the beam, and then right in the middle I've got the force of the beam itself, like that. Okay, that's a plenty good picture to work from right there. We could do something simpler if you wanted to. We could just have the line, and then have F1 and the safe and the beam and the air conditioner and then the wall here. Okay, but you have to draw that picture and say, what forces do I have and where are they? All right, let's get some numbers in here. Notice these are all in kilograms. Kilograms do not measure forces. Kilograms measure mass, right? So we need force. In order to get the force, we'd have to multiply by G. So the beam was 30 kilograms times 9.8 would be 294 newtons. and the air conditioner is 300 times 9.8, 2,940 newtons, and then the safe was 250, making 2,450 newtons right there. Okay, and again, these two are unknown. How big of a wall do we need to build to hold up this beam, this floor, whatever it is? Can we get away with 2x4 studs? Do we need 2x6s? Should we go to some steel, some concrete block? What's it gonna take to hold that up? Okay, all we have to do is run through our steps. Remember that we want to pick a pivot point. And you can pick any pivot point in the world. It does not matter. But I will tell you that if you pick one of your unknown forces, then the torque due to that force falls out. We saw that in the last problem. If I were to come along and pick that as my pivot point, the position where F1 acts on the beam, then the distance from the pivot point to F1 is 0 meters. And you can see that the torque, force times distance, force times 0 is going to be 0. That unknown will go away. I'll only have one unknown in my equation. So very often we pick an unknown force. We don't have to do that. It just makes the math a little bit easier. Okay, let's measure all the other distances then, because that's step number 2. Measure from the pivot. All right, they told us here that the safe was 3 meters from the left wall. So if I start at the left wall, which is the pivot point, this would be 3 meters. For the beam, I need half of the whole length of the beam. They told me that the whole beam was 15 meters. So I'm going to go ahead and put 15 over here, and half of that would be 7.5 meters right there. The air conditioner is 5 meters from the right-hand wall. The right-hand wall is at 15. I need to count back 5. That would put it at 10 meters there. Okay, so now we have picked a pivot point. We measured all our distances from the pivot point. You have to do that every time. All right, next up, we say the sum of the torque equals 0. That's where we want to go next. And I see 5 forces, so I'm going to have 5 torques. I'd have F1 times 0. I'd have 2,450 times 3. Here's 2,900. No, it's not either. 294. That's acting at 7.5. And here's 2,940 acting at 10. And then lastly, I've got F2 at 15 equals 0. Okay? You just want to go left to right along this thing. I've got 1, 2, 3, 4, 5 forces. I better have 1, 2, 3, 4, 5 torques, preferably in order so you can keep them straight. And it's just force times distance all the way through. You can see the only unknown, at least after we let F1 times 0 be 0, is the F2 here. So real simple math to do this. What do we need to do? We need to get our directions of rotation. So I invite you to take your pencil, hold it at the X. So you're holding the left hand end of the pencil between your fingers, and then I'm going to push down where the safe pushes, and that causes the end of my beam to rotate downwards. We're going to call that negative, so this guy gets a negative sign. The beam also causes a downward rotation, negative. What's next? The air conditioner, negative rotation. When I hold my pencil at the X and push up where F2 does, then the end goes in the positive direction. So I put a plus sign right there. We want to solve this for F2. So I'm going to multiply all that mess and go ahead and put it on the other side. 2,450 times 3 plus 294 times 7.5 plus 2,940 times 10. Right here I'd have F2 times 15 equals 38,955. I went ahead and multiplied all this out and then added it to both sides. so that it ended up over there. Clearly F2, all I got to do is divide by 15. So 2,597. We left the units out. That's kind of sloppy, but everything's in newtons, everything's in meters. Here's a force. It better be a newton, right? If you want to put that in there, we put it in last time. You saw how it canceled out. Whatever you want. Okay. I've got this number, 2,000. No, I'm sorry, F2 over here, 2,597 newtons, and we'd still like to know F1. So you got a couple choices. You could pick another pivot point, a different pivot point, maybe F2, and work that. But it's so much easier to turn to the other equation and say, well, I know the sum of the forces also has to be equal to 0. Notice here, this is forces, no distances, right? We use the distance to get torque, but here I'm just adding the forces. So I'd come along and say F1, 2450, 294, 2940, F2. We know what F2 is, 2597. And all that equals 0. Okay, I don't need the distances there. I do need the directions. And this is not necessarily the same rotational coordinate system that we had before. This is an up-down coordinate system. So pretty much anything that points up we'll call positive. Anything that points down we'll call negative. F1 then would be positive. These three in the middle are down, negative, and the last one's up like that. Okay, so again, some real easy math. I'm going to do this on the wrong side here and make everything positive except for the last one, which is negative, and then put it on the other side, if that makes sense. 2,450 plus 294 plus 2,940 minus 2,597 would simultaneously add all those up and put them on the other side and give me 3,087 newtons for F1. Okay. Very often this is the way it works out. Usually one end has more of a load than the other, and if you kind of look at that, it's always good to kind of go back and say, does this make sense? Should this guy really have to hold more of the beam than that one? Well, he's got this big heavy safe that's only 3 meters away. The air conditioner is a little bit more, but see how there's some more distance there? So there'd be less torque due to that. And yeah, it makes sense that this guy would have just a little bit more. Not a whole lot, but a little bit more. So that's a beam problem, and those are good to be able to do. Here's another beam problem. This one's actually called a boom problem. A boom is a beam that is supported by a cable. So typically there will be a wall like this, a beam or a stick sticks straight out, and then a cable goes up. It says here that that cable is attached to the other end. So we're looking at a situation like that. You may have seen something like this on the front of a store, and they've hung a sign out there, the boom of a sailboat. There's lots of places that we use an arrangement like this. You could rig up something off of your shop wall and haul the engine out of your car or something if you needed to. All right, but I've got a stick here, and then there's a cable that's holding that up. This one says there's a little bracket on the left-hand end of this thing, so you could imagine something bolted to the wall with a little pin that went through the end of that thing just to kind of keep it from flying around. But we're supporting it on both ends. We're told that the boom, that stick, that beam, is 15 meters long, and it has a mass of 30 kilograms. We already know that that's a force and that we need to put that in there. So I'm in the middle of the stick. I'm going to come in right here and say that's the force of the boom, like that. So now we've got this guy represented. It's held up at both ends. The wall is either going to push up or down. I'm going to guess that it's an upward force right there. The other end has a cable. That cable actually pulls back this way. And you can see here that that's not a right angle. In fact, there's a 30-degree angle right there. That's going to change something. If you remember what we said about torque a long time ago, if the force is not perpendicular to the moment arm, then you need to toss in a trig function to get the part that is perpendicular. Okay. In this case, we've got the perpendicular would be the opposite, so we toss in a sine 30 in this. I'll show you that when it comes time to do that. But I've got my 30 degrees in there. There's a 250 kilogram mass. It's 2 meters from the right-hand wall. So over here somewhere, I got a big heavy thing that we're holding up. Maybe this is your car engine here. All right. Doesn't say what it is. I'll just call it F mass. Like that. Let's see if we can get some of these numbers. 30 kilogram boom, 30 times 9.8 would give me a mass of 294 newtons. And if I had that 250 kilograms times 9.8, then that would be 2,450 newtons right there. Remember again that these are forces. It should be measured in newtons. Kilograms does not measure force, it measures mass. So that's easy to do. We're going to call this one T, the tension in the cable. And well, you want to just call this W, F sub W, whatever you like. I'm lazy today. Let's call it W. And I've got those 4 forces. 2 of them I know. 2 of them I'd like to know. Like that. Okay. Well, you know that the next thing we need to do is to pick a pivot point. And you know that if possible, we want to pick an unknown point because that knocks that unknown force out of our torque equation. So it makes sense to me to come in here and to pick this as my pivot point, where the wall touches the beam or through that pin, whatever. All right, so I'm going to call that the pivot point. I need to measure the distance from that pivot point to all 4 forces. And from the pivot point to W would be 0. I know that the whole beam is 15. So out here the cable is at 15 meters. The mass is 2 meters back from that. So 15 minus 2 would be 13 meters. And then the weight of the beam acts at half of the length. So that would be 7.5 meters right there. So now we have measured all the distances, and we're doing good, right? Next up, we built the equation. Sum of the torque equals 0, and to do that, we need to look at our picture, and we see that I've got W, which is acting at 0. I've got the boom, which acts at 7.5. I should have put the number in there, shouldn't I? Let me go ahead and get that. Sorry. You can write it all out. It doesn't hurt, but I don't have a whole lot of room today. 294 at 7.5, and I've got 2,450 at 13, and I've got T at 15, but this is where I need the vertical component. I need the part that pushes upward. That's not a force there, but I want that part that pushes perpendicular. T pushes to the left and up. The part that pushes to the left doesn't cause rotation. That just tries to push the stick through the wall. I want the part that's trying to rotate that, the upward part. And since that would be the opposite, this is the hypotenuse. Opposite hypotenuse is sine. So right here I have to toss in a sine 30 and everything equals 0. If your force is not perpendicular, get the part that is perpendicular. All right, right here W times 0 is 0. I hold my pencil at the X, at the pivot point, and then the weight of the beam pushes down. So this one would be negative. The mass is down. That's a negative. And the cable makes the end rotate up. So I'd get a plus sign right there. Okay, if that doesn't make sense, ask me in class and we'll do a whole bunch of them. But that's what you're trying to do. Which way does the stick rotate because of those forces? If the stick rotates down, call it negative. If it rotates up, call it positive. All right. Here I'm going to say 294 times 7.5 plus, I'm making both of those first terms positive because I'm adding them to the other side. And I would get 34,055. Left over here on the left-hand side, I'd have T15 sine 30. 15 times the sine of 30 is 7.5. So I'd have 7.5 T equals, oops, I already had an equal, didn't I? All right, let's take that out. Whoa, big eraser. Okay, and if I take the 34,055 and divide by 7.5, then I'd get 4,541 newtons. That's what the cable has to hold. That's the tension in the cable right there. Okay. Sometimes the problem stops right there. Sometimes they say find the force in the pin. Find the other force. Okay. Well, we've about tapped out what we can do with the torque equation here. So the easy thing now is to turn to the other equation and say, fine, I'm going to make sure that the forces cancel out. And there's the equation. The only real trick here is that I have forces in the y direction, and I also have forces in the x direction. So I probably need to do both of those. Some of the forces in the x direction, what pushes in the x direction? I'd have two things that push in the x direction. The tension pulls to the left, that acts to the left, and the wall is canceling that out, or the pin, whichever one you want right there. Those two cancel out. Those are the only two x forces, so I need to write those in. I'm going to call this W sub x, which will be the wall pushing to the right, therefore it's positive, and then I'd have the tension pulling to the left, left would be minus, and I would have T cosine 30, pen's goofed up again here, equals 0, like that, and I could build that equation right there. I know most of this, W sub x. Let's go ahead and add T cosine 30 to the other side, and I know that T is 4,541. Dang it. Times the cosine of 30 here. Life is just too short for this. 4,541 cosine 30 would be 3,933. Yeah, it's a memory problem with my computer. Ran CCleaner and everything. All right. Let's see if it'll write now. 3,933. Okay. And then I could build the equation in the y direction. And I'm looking at those 1, 2, 3, 4 forces. 1, 2, 3, 4 forces in the y direction. Let's do that right up here and see if we can make this work long enough to get through this. Sum of the forces, the y direction equals 0, please. So that would be W sub y, what the wall pushes up or down on the end of the beam. That's an upward force, so we'll call it positive. The beam is a downward 294. The mass is a downward 2450. And then I've got an upward component of the tension, the y component of the tension. So there's T. I want the opposite, so I'd have to toss in a sine of 30 right there. and this is getting pretty aggravating, so I think you can see where that goes. We've got the equation built. We know what t is, so we can take that and plug it in, and that way we could solve for w sub y there. There is an x component and a y component of that, what that pin has to hold. You'd want to use the Pythagorean theorem to get the total force on the pin. You could do an arc tangent and get the angle that that force has to act at, and that would tell you everything you'd need to know. If you were actually building this thing, you'd have to come along and say, well, how big is, how big of a pin do I have to put right there so that it doesn't break? All of this is about safety. It's about building something that's going to last. And if you don't put enough pin right there, it will shear, it will cut it, it'll break. And the whole thing will fail, and people will get hurt, and people will die, and there will be lawsuits and all sorts of bad things. Okay, so there's 3 examples, and thank you for your time. We'll do more of these in class. There's only 2 kinds: the hanging mass problem, where you let the sum of the forces in the x direction equal 0, make sure the sum of the forces in the y direction equals 0. And then you've got the beam problems, the long stick with forces at different points, and there you need to do some of the torque, and if necessary, some of the forces equals 0. But everything equals 0 in this business. Thank you much.